All right, I'm sorry about my delay on that. I'm not going to go the whole hour today. I just want to give you a few definitions and we'll be sent on our way. This is chapter 2 out of the 4 equilibrium chapters. I know that you've learned some things about acids and bases. We talked about acids and bases back in chapter 4. Chapter 4 was about stoichiometry in water. We had precipitation reactions, we had acid-base reaction, and then we had redox reactions in that chapter. But what you learned in that chapter was not anything really like what we're going to be doing in this chapter. That one was just stoichiometry. How much of a base does it take to neutralize this acid? In this chapter, we're going to look at more of the equilibrium and concentrations of things. It'll be different. Mainly definitions today. Let's take a look. You already know what an acid and a base are. An acid is something that will increase the hydrogen concentration. A base is something that will increase the hydroxide concentration. Acids have a low pH, below 7. Bases have a high pH, above 7. We learned that the pH scale goes from 0 up to 14. That's not entirely true. The pH scale can go below 0. You can have a negative pH. We'll see that later in the chapter. And it's possible for the pH to go up above 14 too. Not common. It's not real. That's not what we normally see. Extreme pHs like that, but it's possible. Those would be very strong acid or base. When we did acid-base chemistry before, we were using what we call the Arrhenius model. Arrhenius was the first person in chemistry history to come up with a definition of what acids and bases are, a model for them. Arrhenius said that an acid is anything that has hydrogen, you put it into water and it releases its hydrogen. Arrhenius defined a base as anything that has a hydroxide, so that when you put it into water, it would increase the hydroxide concentration. It would be really easy if that was the whole story, but it's not. It turns out that acids and bases come to equilibrium quite a bit, and that's not really addressed by the Arrhenius model. It was found as chemistry evolved. Arrhenius lived in the 1800s and was a huge pioneer. I mean, this dude was really, really smart. But he didn't quite have the whole story. As they learned more and more chemistry, they realized that there were some things they could put into water that didn't have any hydroxide in them, but they would still increase the pH. So how can that be? If the Arrhenius model involved bases only having OH in them, there's got to be some other way that the pH could be increased. And that was where two guys, Bronsted and Lowry, together came up with a different definition of acids and bases. Acid's pretty much the same. Anything that gives off a hydrogen is an acid. But the definition of the base, they said that anything that can take a hydrogen is basic. Some of what we do today, you may feel like you've learned it before. You may have in Chem 1. I know Chem 1 is not fresh in your mind right now, but some of this will sound familiar. Conjugate pair, I'll talk about that soon. We don't really have conjugate pairs with Arrhenius. That's why it's not coming up. It hasn't come up before. One of the things that we learned about acids is that you can have strong acids and weak acids. Just a reminder about what those are, and I've done this on purpose. I made my arrow really obnoxious to show that when you have a strong acid, there are only 6, remember. Strong acids dissociate completely. Every single molecule of a strong acid will release a hydrogen ion. So when this thing is done dissolving and reacting, there won't be any of this at all. That will be 0. You'll only have these. You need to know what the 6 strong acids are still. This may not make any sense why I'm saying this, but when we talk about weak acids, it will make much more sense. When this reaction happens and the acid breaks apart, the hydrogen ion and whatever the anion are, they are not attracted to each other at all anymore. There's nothing that would draw them together because they're both aqueous. I know even though they have opposite charges, you got a positive here and a negative here, even so, there's no remaining attraction between those two. So it's impossible for the A to accept the hydrogen. Remember how I talked about the Bronsted-Lowry model shows bases being hydrogen acceptor. This is not able to accept a hydrogen because if it was, then the arrow would not be like that. It would be both directions. But since it's a one-way arrow, it's a one-way reaction. These break apart. They cannot join back together. There was a very famous person that spoke on the behavior of a strong acid. And as they were speaking, I actually was able to capture part of that. And I think it's important for us to hear this. This is a description of the behavior of strong acids. Listen carefully. Listen to it. This is a lecture on strong acid behavior. The 2 ions break apart, and what? They can't ever get back together again. So you maybe didn't know that about this song. You may have heard this lecture before. Good finish, Taylor. But anyway. So the song, yeah, kind of reflects the behavior of the ions in a strong acid. They break apart, and they're never, ever getting back together. So it's a one-way only reaction. You're like, what was that playing for? Oh, that's what I meant. Now here's what happens with a weak acid. A weak acid, notice the arrow. This is more like what we expect. The weak acid dissociates partially. There still is reactant present, and not all of the reactant dissociates. In fact, we only get a little bit of product, and then it stops. Because it comes to equilibrium, we can describe the K value. And when it's for the dissociating acid, we call it Ka. In chapter 13, it was just called KEQ for equilibrium. But sometimes we have specific names for equilibrium constants. We call that Ka. So the more an acid dissociates, the farther to the right it goes, the higher the Ka value. So stronger acids always have a higher Ka. If you have one of the 6 strong acids, their Ka is infinity. So this is not, the Ka is not describing the strong acids, all weak acids. But as weak acids, they could be either strong or weak. Relatively, comparatively. Now, a couple of terms. HA would be considered an acid. It's something that has hydrogen ion. You can see it's dissociating and releasing the hydrogen. When the hydrogen leaves, we're left with A. A is called the conjugate base. So on that previous slide, where I mentioned Bronsted-Lowry gives rise to this acid-base conjugate pairs, that's what I'm talking about. There's an acid. This would be its conjugate base. We call it a base because it's a reversible reaction. If it goes back the other way, that A would be accepting a hydrogen to make that. If you're talking about the anion of a strong acid, you can't really call that a base because it's not able to take a hydrogen. What's the matter?
If it was like more complex and there was like three products, would both of the other products be conjugate bases?
No, only one of them. And you're not going to see anything more than just 2 things breaking apart. The hydrogen and then whatever the anion was. Okay, now the behavior of a base is like this. I'm going to symbolize base just with a capital B. Notice it's weak because it's got a 2-direction arrow there. Now, what's the job of a base? Keep in mind what the definition, according to Bronsted-Lowry, is. A base is something that accepts a hydrogen ion. So the job of the base is to take a hydrogen ion. If you put a base into water, the water actually has 2 hydrogen ions on it. The base is going to take 1 of them. So there you see it. There's the base with a hydrogen ion on it. So this is what people were realizing. You know, the Arrhenius model just shows a hydroxide breaking apart from a positive ion. You've got the hydroxides there to make a base. But the Bronsted-Lowry model shows when you put a base into water, some of the water molecules lose their hydrogens as the base takes them. And when you have a water molecule that loses its hydrogen ion, gives it away to the base, that makes the hydroxide ion. That's what the water molecule is left as when it loses one of its hydrogens. It's just left as a hydroxide. So producing the hydroxide, that's how a base will increase the pH or increase the hydroxide concentration. It kind of did it indirectly. It didn't have its own hydroxide to give off, but it pulled a hydrogen off of water and therefore caused a hydroxide increase. With bases, you need to have water as one of the reactants because the base needs something to take a hydrogen from, so that'll be water. And I want you to also keep in mind, what you're looking for as a base are things like amine compounds. I didn't say this when we did the organic chapter at the beginning of the year, but amine compounds, you remember amines maybe, they're organic compounds that have nitrogen in them. Having nitrogen makes it an amine. The presence of a